Consider a handful of dry clay. It is ancient, weathered silicate rock, a pulverized geological record waiting for a catalyst to reactivate it. Under extreme magnification, the dust reveals an organized microscopic architecture. It is composed of flat hexagonal plates formed by silica tetrahedra, silicon atoms bonded to oxygen, and alumina octahedra. These plates are stacked tightly, like a microscopic deck of cards. When water is introduced, it acts as a microscopic lubricant. The H2O molecules wedge themselves between these mineral layers, allowing the plates to glide past each other without losing their bond. This specific molecular vulnerability to water creates the property of plasticity. It is the physical mechanism that allows us to deform the Earth under pressure, while ensuring it retains its new shape once that pressure is removed. Centering a mass of wet plastic clay on a spinning wheel is one of the oldest tactile interactions in human history. This relationship began over 16,500 years ago with the Jomon culture of ancient Japan. As the Ice Age ended, these hunter-gatherer communities began utilizing the clay deposits left by a changing climate. The Jomon people developed the world's earliest known ceramic vessels, identifiable by the intricate cord-marked patterns pressed into the wet walls using twisted plant fibers. These textured markings provided a survival advantage. By increasing the vessel's surface area, the cord patterns allowed for more efficient heat absorption, enabling the Jomon to boil and detoxify new food sources, like bitter plants and tough shellfish. Mastering this malleable earth allowed early humans to move beyond temporary survival. They were now building durable containers that could stabilize their diet and archive their cultural identity. When clay enters the kiln, it undergoes more than simple drying. The intense, radiant heat triggers a permanent molecular alteration, fusing the silicate particles together into a chemically stable, stone-like material. Advancing this technology meant learning how to contain and recycle that heat, evolving from simple open pits in the ground to complex, enclosed architectural ovens. This led to the Chinese dragon kiln, a massive brick structure built into hillsides to harness natural drafts, allowing for the consistent high-temperature production of thousands of vessels at once. In Japan, the Onigama kiln utilized a tunnel-like design, where the draft carried wood ash throughout the chamber. At peak temperatures, this ash melted directly onto the clay, creating a natural glass-like glaze. Capturing this level of heat was the final technological leap required to transform fragile, water-soluble mud into a durable substance that can survive for thousands of years. Firing also enables the chemistry of glaze, a layer of liquid glass that fuses to the ceramic surface to make it waterproof and food-safe. Ceramicists achieve this by balancing three primary components. First is silica, the glass former. On its own, silica requires temperatures exceeding 3,000 degrees to melt, which is impractical for most kilns. To manage this, fluxes like calcium or sodium are added. They chemically intervene to lower the melting point of the silica, allowing it to flow and form a smooth surface at lower temperatures. Finally, stabilizers like alumina are added. Alumina increases the viscosity of the melt, which prevents the molten glass from running off the pot and ensures a durable, even coating. Beyond the ingredients, potters can manipulate the kiln's atmosphere. In reduction firing, the kiln is intentionally starved of oxygen at its hottest moment. This oxygen starvation forces the fire to strip oxygen atoms directly out of the glaze's metal oxides. When the fire removes oxygen from red iron oxide, the chemical transition produces the iconic seafoam greens of traditional Celadon. This mastery over chemical and atmospheric reactions allowed humans to permanently bind liquid glass to solid earth. When a glazed bowl finally leaves the kiln, it enters the quiet, domestic space of a home. Here, you can hear a highly overlooked property of the medium, the clear, resonant ring produced when the rim is struck. This sound is a result of the molecular fusion that occurred in the heat. Because the fire has crystallized the clay into a dense, stone-like structure, it now possesses a unique acoustic voice. The kiln doesn't just solidify the object's shape, It gives that object a specific, repeatable resonance that will last as long as the ceramic remains intact. The consistent weight, texture, and specific ringing sound of domestic ceramics play a subtle but significant role in human psychology. For a child, these unchanging sensory cues from a favorite cup or bowl serve as predictable anchors. Research suggests that these consistent patterns provide a sense of security and ritual that helps children self-regulate during periods of stress or transition. This capacity for physical permanence and emotional connection is what drew artists like Pablo Picasso to the medium. He produced over 3,000 ceramic pieces, utilizing the clay's durability to archive his ideas in a form that could outlast his paintings. By lubricating geological dust with water and binding it with fire, we create durable vessels designed to carry our memories across generations.